Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 6, 2016. In this particular video lecture, we will be discussing Newton's three laws of motion. Newton's three laws of motion apply to any object which is in motion and any object which is at rest. Newton's first law of motion, the law of inertia, states that any object at rest will stay at rest until an outside force acts upon it, and any object in motion will stay in motion until an outside force acts upon it. So if we focus on an automobile that accelerates to a cruise speed, and then that cruise speed wants to be maintained, it also has to overcome some forces or resistances that are opposing its forward motion at cruise. At cruise, there is no deceleration or acceleration, so it is trying to maintain inertia, either in the form of no motion or in the form of constant motion. So, the tire rolling resistance and the aerodynamic drag oppose the vehicle's inertia during motion. So, there is a slight amount of power input to overcome these resistances opposing its forward motion. Also, if you go up a hill or down a hill, the component of gravity either opposes the motion or assists the motion. So if it was on a cruise control, it would decrease and increase the power accordingly to the road angle, either in elevation or declination. But assuming on a flat level road, the forces that will oppose the vehicle's cruise speed will be none other than the tire rolling resistance and the aerodynamic air drag. Similarly, an airplane air vehicle, once it goes to cruise speed, it will adjust its power setting so that the thrust equals its drag at that given cruise speed. If that thrust was not delivered into the aircraft, the aerodynamic drag would oppose its forward motion and it would start to lose its inertia at constant speed. Conversely, if you were trying to keep something at rest and it was on a table that was tipping side to side, the component of gravity would want to increase a force upon the object trying to stay at rest. Since the object is mass, and since the gravity is an acceleration, there will be an additional force opposing its rest, provided it was on a table that was tilted. If the object was on a flat table and it was meant to stay at rest, then the force in the form of weight is opposed by the platform of the table upward, equal to the weight of the object, keeping it in inertia. Should that table be removed or suddenly disappear, there will be now a force in the form of weight, mass times gravitational acceleration, causing it to not stay at motion. Another example of a force opposing a static inertia, an object at rest, versus a dynamic inertia, an object in motion. Newton's second law of motion is simply the law of force, which states that a mass that is accelerated or changed in speed, either accelerated or decelerated, will translate into a force. This means force is equal to mass times acceleration. If we use the metric system, which is the most accurate way to describe this Newton's second law of motion, we have 1 Newton of force is equal to 1 kilogram of mass times 1 meter per second squared acceleration. When you reach 4.45 newtons of force, that equals 1 pound. So in equivalent US units, that would translate into a pounds per second times a final speed in feet per second divided into gravitational acceleration, and the same effect would happen in terms of deriving pounds force, either in the form of static force or weight or dynamic force to move something, and or a combination of both, where a certain force is applied on the object for which no movement comes forth, followed by movement when more force is added. So there is a static and a dynamic force as well. But in the bigger picture, force is equal to a mass increasing in speed suddenly. Acceleration is not speed, but it is a change in speed. Speed is distance divided by time. Acceleration is that distance divided by time, again divided by time. So therefore, the acceleration is measured in units of distance over time squared. Or, distance divided by time squared is the same as distance divided by time, which again is divided by time. So that's the difference between an acceleration and a speed. Third is Newton's law of motion on the third law, which is the law of reaction, which states that for every action force in a given direction, an equal and opposite reactionary force in the opposite direction will occur. And this is most commonly seen for practical purposes with jet propulsion, because a mass air is accelerated out of the exhaust nozzle in the direction of the jet velocity, but a reactionary force that is equal and opposite to the action force in the direction of the jet velocity occurs in the opposite direction, allowing the aircraft to move forward via the reactionary engine by Newton's third law of motion. So with everything else in the real world, if you were to push on a door or pick up a cup quickly, you would cause a force in the direction you picked up that cup or pushed that door. But really, there's a reactionary force in the opposite direction, which is actually fulcrum to your body. But because your body has so much more mass than the cup or the door, you keep your balance. You don't realize that it is dissipated out, especially with gravity pushing down. Now, if we were in zero gravity environment, even pushing on an object would cause you to go back as well, because there's no gravity to contain and add another vector to add to your stability on the ground. If you see what I'm saying, gravity itself is an acceleration, and your body is mass. You multiply them out, you get force weight. So imagine you remove the component of gravity, acceleration, and you just leave it into the normal acceleration moments of everyday life. If you were in zero gravity, the Newton's third law of motion would really be pure and unforgiving, because everything you do, even a sneeze, would probably push you back against the wall. So the idea is that for every force in one direction, there is an equal and opposite amount of force in the opposite direction. And because there's so much difference in the mass between a person opening up a door or picking up a cup, a lot of those moments of force opposite are grounded out and dissipated, especially with weight gravity assisting. But to keep things very simple is that we see this every day with the jet engine. A mass airflow in pounds per second mass air by weight is suddenly accelerated out of the jet nozzle, and then that translates into force in the direction of the jet velocity. But then there is an equal and opposite reactionary force in the opposite direction, causing the force we know as thrust to push the engine and the aircraft forward. So these three laws apply to everything in terms of motion and everything in terms of bodies that are meant to stay at rest. It is basically the broadest description of everything at rest and everything at motion. From these three laws, the whole industrial revolution, the mechanical, the machine world was born out of. Of course, there are other laws like the laws of thermodynamics, which another video lecture will cover, and the law of conservation of momentum, which is very closely related to the Newton's third law of motion to an extent. So those videos will be discussed in another lecture set, but it is important to understand that Newton's three laws of motion govern everything that is to stay in motion, everything that is to stay at rest. It is basically known as Newtonian mechanics. Thank you for watching this video and have a great day.